In this video, we're going to talk about greedy algorithms. So a greedy algorithm is designed for a type of optimization problem where we're trying to either maximize or minimize something. It's the idea that we'll try to make the best choice at each step. Okay. Now, see, that's in quotes, right? Because sometimes it isn't always the best choice every time. But what we can maybe find is the best choice for certain scenarios. And we should be able to prove that, okay, using counter examples. So let's go ahead and look at some examples of greedy algorithms. And the first one to start with, let's start with money, since we're talking about greed, right? Makes sense. Suppose we want to make 67 cents worth of change with the smallest number of coins possible. So let's design an algorithm to do this. And we're going to use quarters, dimes, nickels, and pennies. Okay, so typically most people, if they're trying to do the smallest amount of change, they're going to start with the largest coin first. So you start with the largest coin. And you subtract out as many of those coins as you possibly can without going over. So if we start with 67 cents, we'll be able to at least use 25 cents twice, right? Take away 50 cents, and that's going to leave us with 17 cents. So 2 quarters. Okay, now I'm going to try to take away as many dimes as I possibly can. And I'm only going to get away with 1 dime because after that, we don't have any more. So 1 dime. Then we'll take away as many nickels as we can. And that's going to leave me with 2 cents. So 1 nickel. And then 2 pennies. There we go. So that's how we could make the change. And the idea is you start with the largest coin and you use as much of that coin as you possibly can, and then proceed to the next coin. Okay. I just realized I misspelled nickel. That's going to bother me. Let me fix it. Come on. Let me erase the L. All right, eraser. It's being stubborn and I don't know why. There we go. See, sometimes you have to remind it can erase. All right. Okay, so here is the algorithm written in pseudocode using values of coins. Now, this does matter which coins we're working with, and we're going to talk about that, where we could say that C1 is quarters, C2 is going to be dimes, and then nickels and pennies. Now, I said that the values will matter. Sorry, that's supposed to be C3. And then C4 is pennies. The values will matter in the sense that you do typically want to go in order. And if you have to skip one, it does cause problems. We'll talk about that in a little bit. But this is the basic setup. So you start with the coin values and they're going in largest to smallest. And then you see how much we can use of the first type of coin and start using as much as you can and then subtract and then keep going, right? You keep doing this subtraction adding thing. All right, so there's our pseudocode. Now, to prove that this actually works, that this is an optimal way to do this, we're going to introduce a lemma. A lemma is like a pre-setup for a proof of a theorem, okay? Almost like a mini theorem. So if n is a positive integer, then n cents in change using quarters, dimes, nickels, and pennies, using the fewest coins possible, has at most 2 dimes, 1 nickel, 4 pennies, and cannot have 2 dimes and a nickel. The total amount of change in dimes, nickels, and pennies must not exceed 24 cents. Okay, so what they're basically saying is there's a few key things here that are important to point out. That the pennies, dimes, and nickels, right, those can't exceed 24 cents. Why? Because the minute it hits bigger than 24 cents, if it hits 25 cents, we can use another quarter. So we're going to use as many quarters as possible until we hit a point where we can't use any more quarters. And that means it's less than 25 cents. So at most, it could be 24 cents. At smallest, it could be 1 cent or 0, right? Nothing. That's possible too. But that's the idea, that no matter what, we're not going to have more than 24 cents left over after we subtract out all of the quarters. And here's what's kind of cool about this. When we compose all of the possible combinations for 24 cents, it'll only need these 2 dimes, 1 nickel, 4 pennies, which I put on the screen just to kind of help us step through. So for instance, for 24 cents, right? If we're going to do 24 cents, we would need 2 dimes, 4 pennies, right? And then the minute I go to 23 cents, I'm going to use 2 dimes and then 3 pennies, 2 dimes, 2 pennies, right? I'm basically just going to use combinations of dimes and pennies all the way up to 20 cents. I hit 20 cents and I'm just going to use 2 dimes. All right. Then I get less than 20 cents, like 19 cents. And I'm like, all right, can't use 2 dimes anymore. I'm going to use 1 dime and I have to use nickel now and all 4 pennies. And there we have 19 cents. And then to do 18 cents, I'm going to have to take away a penny. So just 3 pennies. And then 17 cents, 2 pennies, and then 1 penny. All right. And then we hit 15 cents, which is 1 dime and 1 nickel. And then let's go to 14 cents. And you get the idea. Now we're only working with dimes and pennies again. Okay, 1 dime, all the penny combinations. So we can make every combination of 24 cents just using these coins. Done. Now, they prove the lemma in the book by contradiction. But you could literally just list them all and use the logic that the minute it's over 24 cents, you can use another quarter. Okay, so here is the theorem we're going to use to prove, that's going to help us prove the cashier's algorithm, which is what we were doing before with the coins, produces change using the fewest coins possible when the change is made from quarters, dimes, nickels, and pennies. Okay, so we're going to highlight this proof, and it's a little bit weird with the lemma. It makes it so easy, but it's going to use proof by contradiction. Okay, so here's how we're going to do it. Wow, that's not how you spell contradiction. Contradiction. There we go. All right. So we're going to say that suppose there exists a way of making change using fewer coins than the cashier's algorithm. All right, and let's say it would use Q prime quarters. I'll write that out. Okay, now Q prime is going to be less than Q, which is the number of quarters from the cashier's algorithm. So it's using less quarters, but they're making the same change. So here's the problem. If it's using less quarters, that means it's going to have more than 25 cents left over, because the cashier's algorithm is using more quarters. So there's definitely at least a quarter's worth, at least 25 cents worth left over, which means there is more than 24 cents. But that contradicts lemma 1. So we've already proven lemma 1. Oops. So we're done. Since we've already shown lemma 1 works, we showed all the possible combinations that work, and it's true, that holds. Lemma 1 holds, but you can use a proof by contradiction, which they do in the book. Like I said, you can look at that. But otherwise, we finished it. We've proved that that contradicted lemma 1 because it has to have more than 24 cents, because this has quarters, that it used more quarters. So we know, since the cashier's algorithm is going to come up with the same amount of change, it's just used more, then that's where it used more, and that's a problem. All right, so there you go. Now, I did say this earlier, but if you alter the coins you're looking at, it's not going to give you the smallest coins possible. So if you're not using quarters, dimes, nickels, and pennies, it's not going to always work. So for instance, let's say we want to use quarters, dimes, and pennies. No nickels. So I'm skipping nickels. All right. And I want to make the least amount of change for 30 cents. Okay. Using the cashier's algorithm, here's what it's going to do. It's going to start with the quarters, right? It's going to subtract out 25 cents, leaving me with 5 cents. I can't use any dimes, so the rest is pennies. So that uses 1 quarter, 1 quarter, and 5 pennies. That's 6 coins. But I could have made 30 cents with 3 dimes with these, this setup. And that's less coins. So it doesn't work because we skipped the nickels. So it doesn't work for all combinations. Okay, it does work for quarters, dimes, nickels, and pennies. All right, let's look at another problem that uses a greedy algorithm. Suppose Fred is at Comic-Con and wants to see as many panels and talks as possible. Divide a greedy algorithm so he can attend as many as possible. And here's the things we're going to assume. We're going to assume that once he attends the session, he's going to stay. He can't go to 2 at the same time, but he can attend a session that starts at the time 1 ends. So we're going to assume that he can get to the next session, no problem. All right. Even though technically he might be a smidge late, maybe they always end 1 minute early, then it's designated. And so he's good to go. All right. We're just going to use that for simplicity. So we want to design an algorithm so he can hit up as many talks as possible, meaning like when he goes through the scheduling, we want to make sure that he's picking the schedule based on what is the most he can hit. And let's just assume he wants to go with anything he can. All right. Okay. So one possibility is maybe he looks for the earliest start times. And he picks by early start times. Okay. So let's test this out. This is how we test the algorithm. We're going to see if we can come up with an example that doesn't work. All right. So let's say we have a talk that goes, the first talk goes from 8 to noon. All right. And then a second talk that goes from 9 to 10. And then a third talk that goes from 11 to 12. All right. So if we pick earliest start time, that means he's going to pick the first one, but then he misses out on the other 2, period. And we know that that wasn't the most optimal scenario because he could have attended the other 2 talks. That would have been a smarter way to have done it. So picking the earliest start time doesn't work. So sad face. That one doesn't work. Okay. What if we pick the shortest talks? All right. So in this scenario, it would work. He'd pick the second talk and the third talk, and he would be good to go. Let's see if we can create a scenario where it doesn't work. Okay. So let's say that the first talk goes from 8 a.m. to 9:15. Let's say the second one goes from 9 to 10. And the third one goes from 9:45 to 11 a.m. All right. So using the shortest talk algorithm, he would select talk number 2. And the minute he selects talk number 2, he's in trouble. He can't go to either the first one or the third one because there's overlap and he can't attend more than 1 talk. Okay. But we know if he were to be smart, he would just go to the first one and the second one. I'm sorry, the first one and the third one, and he'd be able to attend more talks right off the bat. All right. So picking the shortest one doesn't work. All right. So here's the one that's going to work. You need to pick it by the earliest end time. Okay. Earliest end time. So let's see what happens in these schedules if we pick the earliest end time. Okay. So in the earliest end time scenario, he would pick the 10 a.m. All right. And then automatically he's looking for the next earliest end time. And both of these end at 12 p.m., but he can't attend the first one when he's attended the second one. So he's going to pick the second one here. So I'm not sorry, the third one. So he's going to select those two based on the end times, the earliest end time. All right. So he got the optimal solution. Yay. No more there. Happy face. Yay. Okay. Let's go over here and see if that works here. Okay. So earliest end time. So first he's going to pick 9:15 a.m. because that's the earliest end time. And then he looks for the next early end time. He's like, okay, well, 10 a.m. That's a problem though, because there's an overlap. So he's like, nope, not 10 a.m. Okay, 11 a.m. is the next earliest end time. So I'm going to pick that one. Doesn't have overlap. And again, yay, he optimized his schedule. So Fred will pick earliest end time, and that's going to optimize the scheduling. And that's what the greedy scheduling algorithm says. Talks about start times, end times, and it picks by the order of earliest end time. All right. Okay, now we're going to get into the halting problem. So the halting problem is very interesting. It is the most famous theorem in computer science, and it's actually unsolvable. And the first person who proposed it was Alan Turing. And if you don't know who Alan Turing is, there are many movies about him. A famous one that was made not too long ago called The Imitation Game. Very good if you haven't seen it. But Alan Turing was like the biggest name in computer science, and he's proved that the halting problem is unsolvable. And here's how it goes. It asks whether there's a procedure that does this. It takes as an input a computer program and inputs it to the computer program and determines whether the program will eventually stop when it runs this input. Okay, so it's this idea that if we put a program into the program, will it run forever or will it eventually stop? That's the question. And it has no answer. It's unsolvable. Okay. And I actually really struggled with how I wanted to explain it. And I found a really great video. This video here on YouTube is excellent. It's very short, 5 minutes. In fact, go watch it. Take a moment, go watch this video. It's so good. It explains it so well. Got cute little pictures. And I thought, okay, you know what? I'm just going to have you watch this video. This diagram highlights the problem. This is from the textbook, but man, I don't believe it explains it nearly as well as that video. And the video even highlights the proof. It uses a proof by contradiction to show that it's unsolvable, that we cannot actually say that it'll give us an answer. All right. So there you go. Watch that, the halting problem, and see the most famous problem presented in computer science.